this video, I'm going to talk about the transfer function. To understand the transfer function, we start with an nth order linear time invariant differential equation. It looks like a sub n multiplied by the nth derivative of y with respect to t plus a coefficient a sub n minus 1 multiplied by the n minus first derivative of y of t, and so on all the way down to a sub 0 multiplied by the 0th derivative of y, which is just y of t. Y of t represents the output of my system. On the other side of this equation, I have b sub m multiplied by the mth derivative of r of t with respect to t, where r of t is the input, plus a sum of decreasing derivatives with coefficients. I'm going to assume that m is less than n, which is needed for the system to be causal. It makes the system strictly proper. Then to further develop this, I'll take the Laplace transform of both sides. What I get is a sub n multiplied by s to the power n y of s plus a sub n minus 1 s to the power n minus 1 y of s plus continuing down to a naught y of s plus initial conditions as the result of this derivative. On the other side, I'll have something similar. I'll have b sub m s to the power m r of s plus b sub m minus 1 s to the m minus 1 power times r of s, and so on, including some initial conditions. In order to compute the transfer function, what we're going to do is we'll assume that all of our initial conditions are 0. As a result, our equations reduce down to exclude those initial conditions, and I'll pull y of s, the output, and r of s, the input, out. If I solve for the relationship between the input and the output, y of s over r of s, I'm left with b sub m s to the m plus b sub m minus 1 s to the m minus 1 plus dot 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 plus b naught in the numerator, and a sub n times s to the n plus a sub n minus 1 times s to the n minus 1 plus dot 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 plus a naught. And this fraction represents what I call my transfer function. I'll call it g of s to be short. If I draw this in block diagram form, r of s is my input, g of s represents the dynamics of my system, and y of s represents the output. This transfer function, g of s, describes the relationship between the input and the output, which describes my system dynamics, and it can apply to many kinds of systems such as electrical, translational, rotational, and so on. To put this into practice, let's do an example. I'd like to find the transfer function represented by the differential equation dy of t dt plus 2y of t equals r of t. To solve this, I'll take the Laplace transform with 0 initial conditions. That'll give me s y of s plus 2y of s equals to r of s, which is s plus 2y of s equals to r of s, or y of s over r of s, which is my transfer function g of s, is 1 over s plus 2. In my second example, I want to make use of the transfer function to actually get the time domain response y of t if the input r of t is a unit step, or u of t. We're going to assume that the transfer function g of s is the same as what we found in the last example, 1 over s plus 2. The first thing I'm going to do to solve this is that I'm going to convert r of t, which is u of t, the unit step, into its Laplace domain representation, r of s, which is equal to 1 over s. I also need to understand the transfer function y of s over r of s, or g of s, can be manipulated so that way I can get the output y of s, which is just equal to the transfer function g of s multiplied by the input r of s. So I'll multiply r of s with g of s to get 1 over s plus 2, and I'll use partial fraction expansion to figure out what the inverse Laplace transform will be. Y of s can be expanded to be a over s plus b over s plus 2. To solve for the a term, I'll take my 1 over s plus 2 and multiply it by s, and then I'll evaluate when s equals to 0. The s's cancel, and so I'm left with 1/2. To get b, I'll take 1 over s plus 2 and multiply it by s plus 2 and evaluate this when s is equal to negative 2. The s plus 2's cancel, and I'm left with negative 1/2. So y of s can be written as 1/2 over s minus 1/2 over s plus 2. By taking the inverse Laplace transform, I can find the time domain function y of t, which is equal to 1/2 minus 1/2 e to the negative 2t u of t. The key result from this example is that if we're given an input to a system and the transfer function of the system, we can easily get the output response. That's all for now. Thank you for watching. I hope that you found this helpful. Ta-ta for now.